Hi class, this week's lab is compounds and their bonds, and this is a good lab, but it's got some information that it's requesting from you guys that will be from future chapters. So I'm doing my best to put as much together to help you understand. None of this should be completely foreign because it should be based on some of your knowledge from Chem 10, but I've put together as much as I can to help you be able to do this lab successfully. First thing about this lab is if you go on lab flow, this lab takes up 2 rows. So I just wanted to point that out, that if you go through this first row, I believe this gives you to the end is the quiz. And then the second row provides you with sample images. I'll come to that part later. And this PDF will also be in Canvas. And then our data support submission. So make sure you're very aware of it. I always post all the sections, so if you're confused or these are too many, just make sure that you follow the list and it matches up, and then that way you've watched every video and you've followed everything you need to. Excuse me. The objectives: write chemical formulas and names for ionic compounds, including polyatomic ions. Write formulas and names of molecular compounds. Write the electron dot symbols. Use the electron dot structure of a compound to predict its shape and polarity. So I'm doing this lecture a little different, this video. I am covering the actual lab first because there's a lot of information, and some people may understand that knowledge a little bit better and not want to go through the whole video. So I'm covering the lab report first because it can be a little confusing at first when you look at it. So when you get to the lab report page, this is the first page right here where my arrow is, and it's asking for an upload. So if you print out the PDF if you're able to, and if you're not, you don't need to. You can write all of this on a piece of paper, but I expect all of this to be detailed out very clearly. If it's not and I can't understand it, you will not get full credit. And just because you understand your writing does not mean that I do. I've had students that have actually typed stuff up. That's fine too. As long as I can read it, I'm perfectly fine with that. Even with this, if you use this, I need to be able to understand completely everything on it. So when you get to the PDF, this should be the first page of the after procedures. And if you're confused about what it is, the procedure part explains everything that needs to be on here. So any part of the lab that you're confused on, go to the procedures and find the title, and the title will tell you what you need to do. So right here it says ion formation. This is ion formation. Ion formation. So just my main thing is make sure you write it very clearly. And this lab has 2 uploads. So this is the first upload, and the second one will be at the very end. Next thing, in this lab, throughout, it's scattered. These are not all together. There are 3 sections about physical properties you have to complete. These can be typed. These typed inside the box, so there's no uploads here. And inside the box tells you the name of every compound. And it's asking for the same thing for all 3. The compound will have the name. It'll ask for the appearance, what you think the appearance looks like, the density, and the melting point. The melting point in this case, I'm going to allow either Celsius or Fahrenheit. All of this information can be found very easily on the internet. If you want to know what these look like to be able to describe in the appearance, the second row has sample images. I will also post this on Canvas, but you can pull up the PDF here and it has each one of these on there. So you can look at that and pull out what you think the appearance is from there. So I'm now breaking down the sections. They may seem like they are repeating, but they're really not. They're all broken down just a little bit differently. So this one says formulas of ionic compounds. Remember, ionic compound is a metal and non-metal. So this one has the name, and you have to put the positive ion, which would be the cation, and the negative ion, which would be the anion, and then the correct formula. Now, this is specifically stating to use the subscript and superscript. The superscript is the top one with the 2 at the top, and the subscript is 2 at the bottom. Yes, you are expected to go through all of this using the correct way that it needs to be completed. So an Na+, this would be wrong, and I would not give you full credit. It needs to be in superscript. S2-, this is not the same as this, and I would mark that accordingly. I did this lab and I did it correctly the entire way through as well. So one of the things about chemistry is if you're going to learn certain things, you need to learn them correctly, and you need to make the effort so that you can retain that information. And trust me when I tell you that if I let certain things slack, it continues on. I've seen it. Names of ionic compounds. Again, I've highlighted that it's specifically stating in the directions to use these, and you would use them here. Here you have the ionic compounds. You'll break down the positive and the cation and the anion, and the name and spelling also counts. This one is ionic compounds with variable charges. So now you're dealing with transition metals. So that means they will have a compound that may have different variable charges to it, and you need to find the correct one. So here is the compound, and you break it apart. Here is the cation, the anion, and the correct name for it. Here is polyatomic ions. So now you have a metal with a polyatomic ion. Same thing as the previous. And yes, the subscript and superscript and spelling, all of that has to be completed correctly to get full credit. And molecular compounds. So now we're no longer dealing with ionics, we're dealing with molecular compounds. Same rules apply. You have to make sure that you have the correct formula. You have to use the super and subscripts and write them correctly. Now we switch from taking the formulas and breaking them apart. You're now doing the name. You no longer have to worry about this part, which is good, but you have to make sure you write these out correctly. And then you write them, excuse me, now you have another one. This looks like another one. Yes, it is. With polyatomic ions and metals. So these are pretty the same thing you're doing over and over. You're just doing it with different subject matter. And now we get to the last page. And the last page has a chart. And it says molecular compound structure, and this is molecular compound structure. You are going to upload this, and it's long. This is not just few. There's about, I think, like 8 or 10 on here. Excuse me. And you are going to fill this out and upload it. You do not need to use the actual PDF. I know some people may not have printers. I understand. But you have to have a piece of paper to upload, and it has to be very clear. Now, we haven't covered polarity yet. You should have covered some of this in Chem 10. We will cover in a later chapter, so I'm not going to count polarity. You do not have to worry about that, but do not leave it blank. Even if it's just a guess, make a guess of what you think it is. We will, in fact, in another lab, have something very similar to this, and you will be expected to know this one. So it's not going to go away. It's going to come back later. But as long as you don't leave this blank, then you will get full credit. Why do I not want you to leave blank? Because you shouldn't leave anything in your labs blank, but I'm not going to count this against you. Molecular shape. This has to do with Vesper. You have also covered that in Chem 10, and I, at the end of this lecture, have information about that. You'll also have a somewhat of a Vesper chart. It's a Vesper chart, but it's not one that we'll use later. I just found one that would make it as easy as possible to do this lab. And that'll also be on the Canvas page. So this ends how to do the lab portion, and it's kind of jumps back and forth, and it's not always clear. So that's why I tried to point out some of this stuff. So now we're going to get into the actual lab. Chemical symbols. By now, you guys should be very familiar with chemical symbols. I'm going to take a step back and make sure everybody understands chemical symbols. They consist of 1 or 2 letters. The first letter is always capitalized. The second letter is never capitalized. If you capitalize both, you're not always dealing with what you think it is. So a perfect example, you guys may have seen this, carbon monoxide is not equal to cobalt. These are 2 elements together. This is 1 element. So we have certain rules, and you have to follow them. In this lab, in this course, there's not a lot of actual writing you're submitting to me. You are more typing stuff up. But when you do, and if you have to upload and you have to write, I expect it to be perfectly clear. If I can't read any of it, or if I struggle, I do mark it, because at this point, when you're in this level, you should be able to write clear enough that somebody should not have to struggle with what you're writing. Another thing I want to go over before I jump into the other sections is understanding a compound. So this one is ionic, but it wouldn't be any different than looking at a molecular one up here. Down here it would be different. Subscript is what's at the bottom. Superscript is what's at the top. Make sure you understand the difference between these, and that could be a big difference. This number here tells you how many are in the compound. This number here tells you the charge for the compound. So there's a huge difference between these. So if we look at this compound here, this is calcium phosphate. This tells me that to have a neutral formula in this, I need 3 calciums and I need 2 phosphates. The parentheses means that this whole compound stays together, and there are 4 oxygens in this compound, but there's 2 of them, so there's actually 8. So you have to make sure you're very comfortable when you see a compound and how to read it and how to break it up and how to understand what a superscript is and a subscript is. Okay, so now we get to ions. Ions, the first ones we're going to start with are metal and a non-metal. That means if you look at a periodic table, you'll have something from one side of the periodic table and something from the other side of the periodic table. If you have a neutral atom, that means that you have the same number of protons and equals the same number of electrons. So same number for protons, same number for electrons, it makes it equal. But if you lose one or gain one, that changes things. So if you have a cation loses electrons. These are the metals. They result in a positively charged ion, which means there's an imbalance. You actually have less electrons than you do protons. An anion, which is a nonmetal, gains electrons and it results in a negatively charged anion. These result in ionic bonding. This is due to electrostatic attraction creates the ionic bond. So you can see a little cartoon here of what happens, and this creates the positive and the negative creates a very strong bond. Atoms will try to have a configuration of noble gases. It's either group 8 or 18, depending on what type of periodic table you're looking at, and they will gain and lose electrons to reach the noble gas configuration. How do they do that? Well, depending on where they are in the periodic table, it tells you if they're a metal or a non-metal or in between. That also tells you how many valence electrons you're dealing with. So in this case, we have group numbers at the top. So if you have a periodic table that reads 1, 2 to 8, that tells you how many valence electrons that element has. If you're dealing with one that says 13, 14, 15, then you simply have to just remove the 10, and that would tell you how many you have. Knowing what type of element tells you if this is going to lose electrons, gain electrons, or share electrons. And you should be fairly comfortable knowing that by now. And if not, you can easily pull up something like this on the internet. I just found this online, and this does make a lot of sense if you understand what you're looking at. And if not, we can always go over it. Metal ions, which are cations, they are positive ions. They lose enough electrons to have the same number of electrons as a noble gas in the row above it. So for instance, if you have magnesium will lose 2 electrons in order to fill the electron configuration of neon. Excuse me. So if it's in group 1, it's going to lose 1 electron, which would give it a positive charge. Group 2 will have a 2 plus, meaning it lost 2 electrons, and group 3 will lose 3 electrons and give it a 3 plus charge. This also affects the electron configuration. So if you have an electron configuration, these numbers all here should match up to the atomic number of sodium, and the atomic number of sodium is 11. But what if you lose an electron? Now you have to actually state that. So what you do is, one, you see a plus here, there's an ion. You have to remove that electron that was lost, and by doing that, it takes up the electron configuration of neon. Over here is just a kind of a visual of what happens when an electron is lost from a metal. You have a non-metal, and non-metals form negative ions. Negative ions called anions. They gain enough electrons to have the same number of electrons as the noble gases in the same row. So for instance, if you have chlorine and it becomes chloride, by gaining an electron, it can take 1 electron on, and that's now going to have the electron configuration of argon, which is directly next to it. So if that happens, group 7 has 1 opening. If they take 1 electron, that gives them a -1 charge. Group 6, which involves something like oxygen, has 6 valence electrons. It has 2 openings, and you have to account for the charges on those 2 electrons that it takes in. So it's 2. Group 5 has nitrogen, has 3 openings, and it can take 3 electrons, so it has a 3 negative charge, and that's important. The number goes first and then the sign. Same thing here with electron configuration. Chlorine has an atomic number of 17, so this should all add up to 17, but it's now taken an electron. You have to account for that. So we add that 1, so it goes from 5 to 6, and now we have the electron configuration of argon. Electron configuration, I put this up. Again, I found this online. A lot of this information you can find very easily online and print it out or save the pages. They do help when you're stuck on learning how to do something. So these are the S's, and anything here will be an S1, S2. It becomes really easy that you don't have to count things out when you understand how these are set up. Over here is 2p, so this would be 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So this is 6. So anywhere in there, you can actually figure out, okay, this is, if you wanted sulfur, it's not going to be 6, it's going to be 3p4. So this tells you how to do this without going into counting everything. And it's a lot easier if you can understand the shortcuts. But if you don't, do it the longer way. Check on these things to make sure until you have it directly, exactly right. Now, energy level will always be in front, type of orbital, and the number of electrons will be in superscript. So here we go. If we look, carbon has an atomic number of 6. This is a neutral atom. So we have 6. It should be here. Is it PS2? It is. And we have a period of 2. So it should end in 2. It should end in P. And it should be at a 2, and it is. So, and we can easily count these up, and it equals to 6. So here again is something that I posted from the previous pages, but it helps you understand how you need to write these out as well. Formation of magnesium. So sometimes you might, I don't know, hopefully you guys do not, but if you do, I'm going to point out why something has a charge and why it's for instance, like a metal. If you look at the overall for magnesium, it has 12 protons and 12 neutrons and 12 electrons. That means it's neutral. But if you remove 2 of the electrons, you now have 12 protons and 10 electrons. There's an imbalance there, meaning that there's more positive charged subatomic particles than there is electrons. So that's where the positive charge comes off of this. So when you write this out, you write magnesium, the number, and then the charge. And when you do naming, magnesium doesn't change. When it comes to first element, you keep it the same. Now we have nitrite, which is nitrogen. This should not have moved over. So nitrogen, you have 7 protons, 7 electrons. That means it's neutral. But when I told you that this is a group 5 element, which means that it can take on 3 electrons. So every time it takes a new electron on, you add a negative charge to it. So this has a negative 3 charge because of the fact that it can take on 3 electrons. Now that it has taken on electrons, it's an ion. You have to change the naming of the second portion of it. So nitrogen becomes an anion when it gains 3. It is now known as nitride. You take the last portion of it, it's usually the last syllable, in most cases, not always, and you replace that with "ide." So this is why it's nitride ion, and when you say that, you instantly know you're dealing with an N3- and not just nitrogen itself. And if some of you get confused why the 3, just remember valence electrons, you're trying to fill an octet. So if you take the group number and you minus by 8, that tells you what it's going to end up being when it adds a specific amount of electrons. In this case, it'd be a negative 3. If this doesn't make sense, any of this, please contact me, reach out, ask questions to other students. We can go over any of this. Okay, formulas of ionic compounds. So how do you put these together? There's 2 ways you can do it, and either way is fine. For an ionic compound to be stable, the positive charges equals the negative charges, meaning that when the compound comes together, it has to be neutral. It has to equal 0. The easiest way to do that is the crisscross method. So you take your sodium, it has a +1 charge when it's an ion. You have an oxygen that is a 2. It's a negative 2, has a 2 negative charge on it, and you simply crisscross these. So what it is that now you need 2 sodiums with 2 plus charges here, a 2 plus charge, and 1 oxygen, and these will cancel out. How do I know? Well, I just did it over here. You take the formula, it says there's two of them, so that's 2 for the sodium, and it has a +1 charge. And I have brackets on these. Now you take the oxygen, there's 1 oxygen, but you have a -2 charge. When you put these together, this is 2 minus 2 equals 0. So they balance out, they are 0. And that's the 2 ways you can do it. You can either do it this way, or you can do it the crisscross, or you can do both of them and make sure that it's the way it should be. Now, there's one rule you need to remember with this. If you break these apart and you have the charges and you crisscross, you must reduce down if there is something that can be reduced down when it comes to ionic compounds only. We don't do this with covalent. So for instance, here we had barium, and it has a 2+ charge, and we have oxygen, which has a 2- charge. When you would write this out, it would be 2 and 2, and we can't have that. You reduce them down to exactly this. It doesn't remove the charges. These are these implied things about chemistry that you're just supposed to retain and know when you look at it. The 2 charges are still there. We just don't see them. And all the rest you can see how you crisscross these out throughout. Now, charge balance with polyatomic ions. Same thing, you break them out with the charges and you crisscross, but make sure that if it's polyatomic ion, you most likely have to use parentheses. I also did the same thing here. We have 3 bariums and we have a 2+ charge. Here we have 2 phosphates, but we have a 3- charge, and still this equals 0. So make sure that you understand that you have the correct charges, and you put the parentheses if it needs it to indicate that the phosphate ion is the phosphorus and the 4 oxygens. You cannot separate these out. Same rules apply. You need to reduce this down. So you see calcium has a 2+, sulfite, this is a 3, sulfite has a 2-. So if you write this out, there would be a 2 parentheses 2. Exactly what you see here. This is not correct because we can reduce this 2 and we can reduce this 2 down. It doesn't mean they're still not there. They are, they've just been reduced down. Transition metal ions, metals with variable charges. Remember that transition metals also lose electrons. However, some of them will have different oxidation states. You need to understand which oxidation state you're dealing with. Your book should have something regarding charges, and if not, you can do a search online for transition metal charges and something should come up. I did find a chart that had them, and I can put that up. However, I have not verified how accurate the information is, so I'm a little reluctant to do that. So here we go. Let's take a look at this. If you ever need to understand which one you're working with here, let's do the reading first. It makes it a lot easier. This is, if you don't see something here and you know that oxygen has 2, that means that this must have been reduced down. If it's reduced down, the iron must also be 2. Here, if you look at just the compound, you read iron. Remember, it's crisscross. So this oxidation state actually goes with iron. This is iron 3 oxide. So if you're given this, you just have to crisscross these across, and this one, because it's got 2 and 2, you have to reduce them down. This is a little hard and gets confusing for students, but the more you do this, the more it makes sense. You can never leave something that's ionic in its non-reduced form. It has to be reduced down or it's marked wrong. And there's 3 transition metals that don't, their charge states don't change, so we would not have to worry about, you know, when you write these out, you don't have to worry about Roman numerals. I'm going to cover Roman numerals in a couple slides up, but this is more about the crisscross with even transition metals. Some common ionic charges. I found this online. Again, it doesn't have all of them. That's why I'm kind of hesitant, but if you remember, under important information on Canvas, I have chem sheets that I put together for you students. There is something in there that doesn't cover all of the ionic charges, but it has some of them, most of the ones that we tend to use over and over again. So again, if you haven't looked on Canvas under important information, there is chem sheets that I provided for you, and it's got the basic foundational information from chemistry, and it includes naming and so forth in there. Names of transition metals. Since we were talking about transition metals, I just decided to stay on this. One thing you need to know, in order for this to be proper, and Being online, I see a lot of people not doing it correctly, even instructors, and I don't know why. When you write something out, when it's a transition metal and you are using Roman numerals, there is no space between the name and the parentheses. There's only a space between the second element. So this goes with the element in front because that's part of the charge that goes with it. So they have to be together. Here I've enclosed Roman numerals to help you understand how to write these out and how do you write them out. Exactly how you see it. So let's take this one here. I would write iron because it's the first element. Oxide is the second, but I need to know what the charge is. You also do the crisscross method to understand what the charge is. So here I take my iron. I look down here. This is 3. So this is iron, 3, oxide. Here is iron, would be my first element. Oxide would be my second. I look here and I don't see anything, so I need more information. But I know that oxygen normally has a 2 negative charge, which tells me because there's nothing here, this must be iron 2 because this had to be reduced down. And that's normally how you do it. It's not overly difficult. The hardest thing is probably remembering the Roman numerals and that the parentheses goes with the first element. Here I've also included a list of some of the element names to help you if you needed that. And notice all the parentheses are next to the metal. There is no space. I expect you to write it correctly. And spelling does count. All right, naming metals with fixed charge. So this is the ones that we probably learned first. There is a space between the metal and the non-metal. And the first element stays the same. Even if it's a cation, we don't indicate that here. So even if magnesium is 2+, we don't do anything with it. The only time that we use prefixes is with molecular, and we'll come up to those later. With these, you just have to know. What do I mean? Well, if we look at magnesium, this has no indication that there's a 2+ when it's a cation. It also doesn't have an indication that sulfite is a 2-. It just says magnesium sulfite. So you don't know the actual charge. This is where chemistry, you just have to know certain things, and you know that by practice and by learning. So when you deal with ions that are metals with fixed charge and non-metals, we don't indicate what they are. It's something that you're expected to know. It's a secret club of understanding it without it being specifically written. So phosphide, if you see phosphide, it's got a 3 negative charge, but nowhere in the writing does it state it. You're expected to know that. Now we get to covalent compounds. Covalent compounds are very different. We use prefixes on both of these in order to understand how many we have. We do not reduce these down. What you have, if you have a subscript of 2 with the first element and a subscript of 4 with the second, you leave it. You do not touch it. So first element retains its original name, but you may have a prefix in front. Second element, same thing as the previous ones. The ending ends in "ide." That's how you know something. It's been changed. There's something different to it. And also a prefix if it needs it. Base name plus "ide." When you have something that has 2 vowels, in most cases, so for instance, if you had monoxide, which we don't necessarily, we don't have 2 O's in it. One of the O's would be dropped off. And usually, we tend to drop off the second vowel that goes with the base is the one that's usually dropped off. But there are cases, unfortunately, there's always exceptions to everything. So here is a chart. I found a little chart that would help you understand how to break this down more if you needed to. So what this ends up being is you need a prefix in front of the first element. You need a prefix in front of the second element. You need to know what these are. In the next slide, I have those. This is a di, so this would be dinitrogen, and this is a tri. So you would take the base of it, oxide, which is just oxide, so we actually don't need to do anything to this one. The oxygen's been taken off, the ending of this, and then tri. This is an exceptional rule where both vowels stay. Why? Because you need the I there in order for this to be tri, so you know it's a 3. So I've included the prefixes so you understand what these mean, but a perfect example, would be right here of pentaoxide. You have penta with an A and you have oxide with O. We do not keep both of them. We drop one of them. And in this case, we would drop the A and leave the O. So this would be pentoxide. So it's kind of weird. Sometimes we'll leave one vowel and sometimes we'll leave the other vowel. The more you get to see these, the more you're comfortable with, the more they just intuitively, you make sense. You know which one you have to drop off. Electron dot diagrams. So now this has to deal with valence electrons. I have a list of valence electrons for the groups that will match. We're not worrying about transition metals or anything like that. These are just fixed variables of metals, fixed charge metals, or non-metals. And you draw them out. So for instance, chlorine has 7, so you would draw 7 electrons out. If you needed to put water together, oxygen has 6. Hydrogen and hydrogen, remember, it has 2 spots. It can take those 2 spots, and you simply draw out the whole compound. If you don't want it to use 2 dots, you can use a line, but they represent the same thing, and it makes it a little cleaner to look at. So this is the last portion, or almost last portion of this lab. You have to write out the chemical symbol. You'll have to find the number of valence electrons. You draw the valence electrons in the following configuration, and then you put it together. So I also have a video that I'm going to put on up for this. The video is how to make these electron dot compounds easier for you. I put this video up for a later lab, but it might help for some of you who are absolutely lost with electron dot diagrams. So I'm going to also put that video up as well. Covalent compounds. This is just another visual, so you can remember that every compound should have 8, with the exception of hydrogen. Everything should have 8 around it. If it doesn't, then that means you're going to have to move some electrons around to either create a double or triple bond, but you also have to make sure that that compound can actually handle a double or triple bond. Covalent compounds, they can exist as single bonds, double bonds, or triple bonds. So this is a perfect example. I've given you some examples of how some of these things look. And sometimes it's easier to put lines because it makes it look a lot cleaner than without the lines. But here's examples of double and triple bonds. And in the video that I'm going to put up, it handles most of these as well, the answers about double and triple bonds. Valence shell electron pair repulsion. This is the last page that of your lab. We're also going to cover this later, but I decided that it would be more beneficial if you actually work on some of this now, so it's not so hard when we come up to it in the lab. So valence shell electron pair, it goes with electron dot, because once you figure out how to put it together, you need to know what the shape is. Why would you need to know the shape? Because molecular shape can be determined by the number of electron pairs present. Electron pairs tend to repel one another. So this VSEPR helps that. It puts it in the shape that minimizes the repulsion between all the electron pairs that are on there. Multiple bonds are counted as single electron pairs, and bonded electron pairs as a single pair. So what this means is that when I show you the chart, regardless if you're looking at a single, double, or triple bond, it's counted as one bond. We don't worry about what type of bond it is. Lone pair electrons have the maximum repulsion, and bond pairs electrons the minimum. So all electron pairs assume positions of least repulsion. This is why VSEPR exists, because we need it to be in the most stable shape with the least repulsion between the electrons. And the last but not least is what takes up the most space is a lone pair, lone pair. Lone pair, bond pair, and bond pair take up the smallest amount of space. As we go into this eventually in another chapter, it will make complete sense. So the last part of this VSEPR chart is it's asking you to find the shape of the compound you put together by electron dot structure. So I'm going to explain this. This is a very simple one compared to what you'll use later. This is a coordination number. I'm just going to tell you that this is bonds. Just look, you have a central atom, and you're going to not count the central atom, but the bonds, the actual, not lone pairs, but the actual bonds here. So I have three bonds around the central atom. And then I look up here and I look at lone pairs. And why am I doing this? Because there's going to be, in your quiz, they're going to ask some of this information. So this will help you to answer those questions. It will tell you how many bonds a compound has and how many lone pairs. And you simply look across and it'll tell you what shape that compound is. And then at the end in the chart, you actually have to tell what this is as well. So, for instance, linear has a central atom, but it has 2 bonds. no lone pair. So it's linear. But let's go down to 3. Let's say I have 3. So here I have 2 different types, okay? Here I have 1 lone pair, and it makes it angled. And then if I go here, now let's go down to, sorry, I'm trying to find the specific one. So the yellows mean lone pairs. So if I go to 4, I go across, but I have 2 lone pairs. So let's say I have, I'm messing this up, I apologize. In this one I have 4. So I have 4 connections. Let's put it as connections. I think that's easier. 4 connections, but I have 2 lone pairs. So when I look at it, I have 2 lone pairs. This is 1, 2, 3, 4. 4 connections overall, but 2 lone pair. This tells me I am angled. Angled in lab flow means bent. Water is bent. So this is how you do it. So I apologize. I made this a little bit not as easy as it should have been. If you have 3, it doesn't matter how many, it doesn't have to be bonds. It could be lone pair. Think of this as connections. And if the connections are 1, 2, 3, but one of those is a lone pair, it's going to be angled. If you have 3 connections on a compound, but 2 are lone pairs, you go across, and 2, it's going to be considered linear. So these are ways to determine this. So I was wrong here, and I'll need to make a correction on the slide for us. But think of this as connections, and then count how many lone pairs you have, and that's going to tell you what the shape is here. So the yellows are the lone pair. Sorry, I thought I looked at this better, and apparently as I'm talking I didn't. Not as well as I should have. Maybe it was a little confusing to me. Anyways, if you have any questions about any of this, please ask me. Hit post a question on Pronto. Remember, I have open office hours. I have student structure sessions, and between Tuesdays and Thursdays I will have my phone app open to Pronto in case anybody needs my help between 4 and 5. And that's the end. So if you have any questions, please ask.